Hi, my name is Yagi, and in this video, I'll be going over capacitors and capacitance for AP Physics C, and by the end of this video, you should be able to figure out the voltage, the charge, capacitance, etc. for all the capacitors in this schematic. And yeah, so to start, capacitance and capacitors, first of all, is a device that looks something like this usually, and what it does is it stores energy via an electric field between two conductors. And capacitance is the measure of the ability to store charge per unit voltage. So capacitance is given the letter C, and it equals to the charge divided by the per unit voltage, so delta V. And if we look at this dimensionally, right, charge is C, voltage is V, C divided by V, which is given the unit farads, or F. Okay? And the main thing to know about capacitance is that it's only affected by the geometry of your two conductors and your overall capacitor. So by geometry, I mean that the distance between the two capacitors, the area of the capacitors, and in the future video, I'll talk about the dielectric material. All of this affects the capacitance. What doesn't affect capacitance, though, is the actual charge or amount of charge of the capacitor. Okay, so now for AP Physics C, you need to know three kinds of geometries and three kinds of capacitors. And the main type you really need to know and get master, I guess, is the parallel plate capacitor. So parallel plate, we have two parallel plates charged, right? Charge density positive, charge density negative. And we know from the previous unit that we're going to have an electric field that's uniform like so, and the delta V, the change of voltage, is equal to this electric field times the distance between the two plates. We also know that the electric field is equal to the charge density divided by epsilon naught, which equals to Q over A epsilon naught. Therefore, we can set that this equal to electric field is equal to the change in voltage divided by distance. We can set these two equal to each other, and what we do is if we divide this by Q divided by delta V, that's capacitance, right? So capacitance over A epsilon naught is equal to 1 over D, and we can then move over this to this side, and we get the capacitance of a parallel plate system is equal to epsilon naught times the area divided by distance. So important thing to note is the area, right? Whenever we're looking at capacitors, we're looking at the area of only one of the plates and the charge of only one of the plates, right? Because in this system, this would be Q negative, this would be Q positive. So the total net charge is technically 0, but whenever we're doing these formulas, right, we're only looking at the attributes of one of the conductors in that system. So that's the formula, and we notice it doesn't rely on anything except the geometries, right? Area and distance, that's all it relies upon. Next, let's go into spherical conductors. So spherical conductor, we have a sphere in the middle, and then we have a hollow sphere on the outside. Okay, and let's say we charge this to Q, charge this then has to be negative Q, right? So it has to be equal in magnitude. And we know from, just what we learned before, there's going to be an electric field between these two conductors, like so, right? Gauss's law. And so this electric field stores energy and therefore is a capacitor. And so the formula, if we want to figure out the capacitance, right, we first need to find out the voltage, right? Capacitance is equal to Q divided by delta V. So the voltage, right, we know the formula is equal to negative integral of E dot dl. So we're going to take the integral, right, from RA, which is the radius of the inner sphere, to RB, which is the radius of the outer sphere's inner surface, from here to here, right? And if we take the integral of that, where I'm not going to do this on camera because it's going to take a little bit, but delta V, we should know, is equal to Q over 4 pi epsilon naught times 1 over RA minus 1 over RB. We can combine these and we get RB minus RA divided by RA times RB. Now if we plug in delta V into here, what happens is the Q's cancel out, so this Q and this Q. We get that 4 pi epsilon naught RB times RA divided by Rb minus Ra, and that's the formula for the capacitance of a spherical conductor. And again, it only depends on geometry, right? Rb and Ra is the only thing that affects the capacitance of the system. We also have the capacitance of an isolated sphere, which is just a single sphere that's charged. And you might be saying, where's the other conductor? The other conductor we assume to be infinity is the other conductor in this system. So for this, idea is that 1 over Rb, right, is going to approach 0 because Rb is at infinity. And so therefore, if we look at this equation, we take the limit of that, we get that our capacitance is equal to 4 pi epsilon naught times the radius of our sphere. And that's for an isolated sphere. And finally, the last geometry we have to go over is the capacitance for a coaxial cable. So a coaxial cable is a cable that has two conductors in it. So it has a conductor on the outer surface, and then it has an actual conductor, like a rod, on the inner surface, and it has length L. So if we take the cross section, right, geometrically, it's pretty similar to our sphere. So we're going to have an outer, inner. The inner, let's say, has charge of lambda. The outer has negative lambda, right? Charge per length. And again, we're going to do the same thing with voltage. So for this, I'm not going to show the whole steps, but the voltage from here to here, the change in voltage, is equal to lambda over 2 pi epsilon naught times the ln of Rb over Ra. Again, Rb and Ra mean the same thing as before. And in this case, right, we want to say capacitance is equal to Q divided by delta V. And so lambda is equal to Q divided by L. So we can plug into there, right, that Q divided by 2 pi epsilon naught over L, the other stuff. And so what happens is the Q cancels out again, and we're left with 2 pi epsilon naught L divided by the ln of Rb divided by Ra. And that's the formula for capacitance of a coaxial cable. Another way it's often written is capacitance per unit length, because that makes them more standardized, right? We're then able to compare the capacitance of different cables. That's just, you divide this side by L, 2 pi epsilon divided by ln of Rb divided by Ra. So that's all of the geometries of conductors capacitors that you need to know. Next, how do we find the actual energy of a capacitor? Well, first of all, let's consider how a capacitor actually charges. So capacitor, we have a battery, right? In a circuit, a battery is given by this long line, which represents the positive, and a short line, which represents the negative, and it's connected to a capacitor, like so. And this capacitor, right, what's happening is we take electrons from the negative section, we're moving them over to here. This electron then kicks off another electron here, and it goes back to positive. So for the first electron, this requires no work because there's no electric field at the capacitor, right? So there's no electric field. So no work for the first one. But as soon as we get this electron onto here and this electron away from there, we get a little change in voltage, little v, between the two. And this causes the next electron that we move to require work. It requires energy because there's a v between the two plates. And so the total work, right, if we keep moving them all in all, is going to equal to, right, this is total charge Q. This is going to be negative Q. This is going to be positive Q, total charge. So our total work is going to equal the integral of the little v with respect to dq. And if we integrate that, we get that work for moving all these electrons, right, to this plate and moving all these electrons away from that plate is equal to, what's also equal to potential energy, right, is equal to Q squared divided by 2C. And again, Q is just one of the plates. Now if we plug in, right, Q equals VC and this formula into this, we can write it as CV squared over 2. And we can also write it as, if we plug in for C, QV over 2. So these all mean the same thing. The main formula is this one, Q squared over 2C. These ones we can derive just by plugging in like so. And this tells us the energy of a capacitor, or potential energy. And then finally, we also have the idea of energy density. And like the name suggests, this tells us the amount of energy per volume of the capacitor. And we calculate this by, again, CV squared over 2, we'll use this formula, times the volume, the volume of capacitor we consider, right? It's going to be distance here, the area of the plates, so A times D, so 1 over AD. We know that C is equal to, for parallel plates, it's equal to Q over, sorry, not Q, epsilon naught A over D. And we know that V is equal to E times D, so E squared times D squared, electric field, right? So what happens is the D's cancel out, and the A's cancel out, and we're left with the energy density is equal to epsilon naught times electric field squared divided by 2. And again, this formula and this formula, even though we derive it for parallel plates, it works for both parallel plates and any type of capacitor, right? Energy equals this, energy density equals that. Next, let's go into parallel capacitors and series capacitors and the differences and stuff. So for parallel capacitors, what we have is again, a battery that provides the voltage and charge, and we have two capacitors or multiple capacitors that are connected via branches, right? So these two capacitors are in parallel because they're connected to the battery via a branch. So if we consider again the charging thing I mentioned before, how it charges, this electron is going to go all the way here and here, and so this whole wire on this bottom side has the same voltage, right? And this one has the same voltage as well, this top side. And so therefore, you can see visually that this delta V of the battery, the change in voltage here, is equal to the change in voltage here and the change in voltage here. So call this 1, capacitor 1 calls capacitor 2. The voltage of capacitor 1 is equal to the voltage of capacitor 2, and this is an important thing to realize for parallel conductors. We also have this idea of equivalent capacitors or equivalent capacitance in circuits, and the equivalent capacitance, what it represents, is a hypothetical capacitor that could represent a system of capacitors, right? So the idea is we could take these two capacitors and represent them as one, big capacitor, and that capacitance would equal the equivalent capacitance. So for this system, the equivalent capacitance times our voltage is equal to our total charge, and this is actually true for all capacitance systems. Okay, and so looking at our formula, right? Therefore, right, so this one, the total charge is equal to, right, our formula C1V1. This one is equal to C2V2. So if we consider that Q is equal to C equivalent voltage times, right, plus this has to equal their total charge. So it equals to C1V1 plus C2V2. And V1 equals V2, so we can call this V, right, because it also equals V as well. So C1 plus C2 times V, the V's cancel out, and so our equivalent capacitance is equal to C1 plus C2, and more generally, our equivalent capacitance in parallel is equal to the sum of all our capacitors, or all our capacitance. And that's an important formula to also recognize. So those are two important things to recognize. For a series capacitor, we have a circuit, and the capacitors go along like straight. They don't have like a branch. There's no choice. So for here, our total charge here, Q2, QT, is equal to our total charge for each of the capacitors. So for here, the voltage is all equal. Here, all the charges are equal. The capacitance, 1 over the equivalent capacitance, is equal to the sum of 1 over all the capacitance. And so, in other words, the total capacitance is equal to the inverse of this sum. And so in this case, right, we want to figure out the total capacitance 1 and 2, right? So we want to first figure out, we know that 1 over total capacitance is equal to the sum of this plus this, 1 over that. So 1 over C1 plus 1 over C2. So this is C1 plus C2 over C1 times C2. And then we flip it to find the actual equivalent capacitance. So C1, C2 over C1 plus C2. And this is an important formula to recognize, right? For two capacitors in series, that's the equivalent capacitance. And this is also important in that as well. Okay, now finally, we can try to solve this problem that I was talking about in the beginning. So just to go over the steps to solve this problem, right? The first step, when we have a problem with this, with a circuit, we want to figure out everything about it. The first step is we want to start with the most complex section, and we want to figure out the equivalent capacitance in the entire system. Then, once we figure out that, we want to go backwards, so go in reverse from that section, and then figure out the V's and Q's of all the other capacitors in our system. Okay, so let's try doing that. So first thing, the most complex part in this system looks like this series section here. So we have capacitor 6 and 3, and so we can combine them, right, using the formula that the capacitor series is equal to 6 times 3 divided by 6 plus 3, which is 2. So we can redraw this circuit like so. So 20 volts battery here, right? So we have 2 microfarad capacitor there, and a 4 microcapacitor or microfarad capacitor there. Okay, and these two are in parallel, so therefore we can redraw this, right? Because in parallel the capacitance is added, so we can redraw this like so. So our total capacitance is equal to 6. And so a helpful thing to kind of like write down all our data and just like be able to solve, especially for problems with more capacitors, like 5 or 6, is to make a table. And to make the table, what we do is I'm going to say C is a column, V is a column, Q is a column, and U is a column. And the special thing about this is that what we can do is C times V is equal to Q. So we can multiply this by this to get this, or obviously divide this by this to get that, or divide there and there. We're also going to create a row for our equivalent capacitance at the bottom. And for each of them, we're going to label all our capacitors. So let's call this one capacitor 1, capacitor 2, and capacitor 3. So capacitor 1 is 4 microfarads, capacitor 2 is 6, capacitor 3 is 3, and we just found out their equivalent capacitance is 6. We also know that our total voltage, right, is 20 volts. We said that before. So therefore, our total charge is 120. Okay, so now let's work backwards. So our total voltage is 20, and this is in parallel, right? Which means that this voltage 20 applies to here and here. So our voltage on our first capacitor is 20, therefore our total charge is 80. Then if we look at this one, right, we can see that Q is going to be equal to, our Q total for this section is equal to our equivalent capacitance times voltage. Equivalent capacitance is 2, the voltage is again 20 for this section, so our Q total is 40. We could also find this, right, by saying that, okay, it's 80 here, total is 120, therefore 80 has to be here, 40 has to be there. Another way of finding that. And we also know that this is a hypothetical capacitor, right? But the capacitors that make it up, this and this, are in series, and therefore they have the same charge as the total charge. So they both have 40, sorry, wrong column. They both have a charge of 40, right, because they're in series. Now we can find out our voltage just by dividing 40 divided by 6, and that's what makes the table useful, right? You can just figure out just by looking at it. So 40 divided by 6, that equals 6.7. 40 divided by 3, that equals 13.3. And finally, we can then find our energies just by doing VQ divided by 2. And so 40 times 20 is 100. 20 times 6.7 is 134. And then 20 times 13.3 is 266. One thing to notice also is this is 60 times 20, so 1200 is our total energy, right? And if we sum these all up, we get 1200. So this equals this. So the sum of all our energies for each capacitor is equal to our total equivalent capacitor's energy. But these don't electrically add, right? These doesn't electrically add, this doesn't add, and this adds, but that's only by chance. So this, and this don't add numbers, but this adds to this. So you can check your work by just adding up all of these and checking like that. But you might be saying, why don't these add? Well, the reason why is because what we're doing is we're not adding them numerically, we're adding them electrically. So if we were to electrically add that column, right, considering it the circuits and stuff, they would technically add to our equivalent, but they don't add numerically. And yeah, that's capacitors and capacitance for AP Physics C. Thank you guys all for watching, and I'll see you guys all tomorrow. Bye.